Okay, so this is supposed to be the summary of my analysis of this article published by Brian and Sigal Walk. So Brian, basically, we've been discussing about this in Twitter for quite a while. This is just the latest article of a series of articles where he discusses these kind of classification algorithm, where he goes in and calculates some, pre-calculates some angles, and then we'll go into these right now. So builds a quantum circuit that implements the swap test. And I think my critique to the article is that you don't need this, right? Because if the way that you encode it is like that, so you have this using the same gates and using these angles, it's just enough if you compare the angles. So you don't really need to go through the actual quantum computation for these. Um, and what I did in the previous videos is basically I kind of try to reproduce what he does and he explains in the article. So what I did was I took exactly the same data set and did a bit of the same pre-processing he does classically as well. So what he does is he takes the averages of each class. So this is the MNIST data set, or a version of it at least, that's already in CSV. And so I think each class each class can has like a 784 pixels. So there's the 784 values in here for each of the labels, and these are the averages of these. And then he goes and compresses this a bit more and compresses this to 16 different values. So he basically does a 4x4 sort of low resolution image of those numbers, so to say. And these numbers is what he then, these are normalized values between 0 and 1. So what he does is, I believe so, is he takes these and he turns that each pair of two of those angles, puts them into a U3 gate, and that's how he encodes the gates that you see in here. That's how he creates those gates. And what he claims is that, well, then the subtest kind of tells you with a certain probability to which class, because what he does is the first 8 qubits here at the top represent the averages of the classes, and then at the bottom you have one new instance, randomly taken from a new data set, and he compares it with the averages, right? Um, let's put that aside, the accuracy of the idea. Let's put aside, um, whether this makes sense or not, whether this is better than a neural network or not. I'm going to keep all this discussion aside and just basically try to prove, that's what I did in the past two videos, that if this is the setup, you don't need to run the swap test. This is totally useless in here. So you just can compare the angles. And actually, it ended up like, I really wanted to kind of keep this as a summary if I really want to do it. So it ends up, the proof is actually fairly simple. Well, at least a proof that is simple enough is what I write in the notebook at the end, um, where I basically say that, if the subtest outputs 0 with probability 100% only when the states being compared are equal, right? And regardless how you created the states, right? So basically, if the states you're creating are equal, then you're going to have 100% probability of classifying, that new data point to that new class. And so, basically, that doesn't really need any formal, I think, proof in there. If you are using the same gates here for the data register and for the test register, the U3 gate, the RY gate, whatever you want, the same gate, and the parameters you're using are the same, this is the only setup where you would have kind of, well, the same, you know, um, the same vectors, right, or high dimensional vectors, right? Because the if the angle of this qubit is the same as the angle of the gate in this qubit, then effectively the matrices of these gates are the same, and so they're going to generate the same state. And if you scale that to the 8 qubits, the same here, right? So if the angles and the parameters are exactly the same here and here, then you're guaranteed to have the same state. So and it's kind of a known fact that, like, there's only, if you restrict the parameters to be between 0 and pi, right? So you don't like allow for cycling or having 2 times pi or 3 times pi or whatever. between 0 and pi, then there's only one way to generate one particular state. So you know, it's not, you cannot get to the same state by parameterizing the gate differently. So with these two facts in mind, you know, that's basically the idea. That's the idea I used to prove these here. So by just running this simple proof in here. What I also did in the previous videos is kind of took a look at a bit more in detail at the function of, you know, what really mathematically the swap test is doing is this part here. So the probability of measuring 0 is defined by this equation. And so, you know, I kind of developed this idea for 2 qubits. So comparing two 1 qubit states. And kind of analyze the way this looks like, and you can see here that this proves the point where exactly in the diagonal where the angles are the same is where you have the maximum probability, and then everything else smoothes out gradually. In the notebook, I played a bit more with, you know, more dimensions, and you kind of, you know, get this pattern within the formula where you have sinuses and cosinuses multiplying. You know, I can't plot so many dimensions, but I can show that I forget about these, but I can show here that if you're kind of replacing all the parameters by the same angle, that's where you're getting it. And I think I can even go farther than that and say, like, the angles don't have to be the same, like all of them. The pairs have to be the same. So if you change this angle must be the same as this angle must be the same as this angle, etc., etc. But that's kind of, you see the point here, right? So this is where you get everything like with a value of 1. So you see all the 1s in here. 1, 1, 1, 1, 1. These other things in between are the angles that I'm using. And I think that's it. That covers the proof. I mean, I don't know. Maybe it's not super crazy hyper formal, but I think just tinkering with the numbers and the equations kind of at least gave me confidence enough that you don't need the swap test. And like, it doesn't matter how many qubits you want to put in there. It doesn't matter how you want to map things. As long as you use this encoding strategy, you don't need a QPU. Okay, so you just compare the angles. And basically, here I use the compress. So I copy pasted the values from the CSV file. So I use the compressed version here. But I mean, like, if you use the compressed version, you kind of see that it literally takes, and that's a code that calculates the Euclidean distance. Okay, just the distance between the two. Let's assume those are points in this high dimensional space. So it basically does this, and it classifies this new test, which is like a sample taken from the label 0, classifies it as a 0, and here you have the distances to different classes. Brian also kind of mentioned that, yeah, well, you know, what if you do not compress? Like, then you will not be able to do it classically. Well, then here you go. So I actually did it. So I actually took the same values, but like uncompressed. So each class has 784 pixels, and the test one has also 784 pixels. So this is about like, yeah, so if I do this, okay, now it's there. If I now go and run the calculation, because I just replaced the variables, and like, it's a for loop, it's a one-dimensional for loop, and then there's like the norm to calculate, like this thing calculates the actual distance. So it's just like a subtraction, and like of the array. So this is kind of maybe another nested loop, right? What it does is it compares. I mean, you're comparing literally like every pixel. I don't know. Maybe this does like max like 5 million iterations or something like that altogether. I think if you multiply 784 times 784 times 10, is that it? I don't know. But again, so let's check first. Let's print test to make sure that it's the right one. So this is the one with 784 pixels, right? And could I plot this to see that it's a 0 or whatever? And yeah, and if I just now basically run this, well, it just takes It takes a ridiculously short amount of time, right? And it tells me already all the distances to the different classes, and it's still a 0. Although, to be honest, as you can see, the distances are pretty similar, so I think we're quite lucky. But the point is like that beast on a simulator takes like 4 or 5 minutes just for the just for like 8 qubits or 16 qubits in total, right? And even if you'd have like a million error corrected qubits, that could, you just compare the angles. So yeah, that's basically it. That's basically what I did. I'm quite happy with the results. I did learn uh, some little nuances while building these expressions in here. So I'm happy that I learned more about like how to actually build, how to actually compose things with the tensor product. Like, knowing that I want to apply this operation, for example, to the second qubit, not to the first qubit, I have to do it with the tensor product. And I'm going to definitely do another video on these because I think there's some kind of interesting points about using linear algebra as a modeling tool for a quantum computation. So I think that makes it a good executive summary. I hope what I said was understandable. If not, questions below in the comments. Happy to answer. And I'm also going to just push this into GitHub so people can play with this as well. Not the CSV file though. Cool. See you next time.